Hi there, it's time for reading quiz 6 on volumes. This is a pretty extensive reading quiz, so I'll go through a lot of the different types of volumes that we'll see here. This is a pretty fascinating and visual subject, and after you get the principles, it's actually pretty easy to apply. So let's talk about those principles. We did a little bit of this earlier in a lab. We're going to start out with what are called solids of revolution. And the principle of our volume rotation is that we're going to take functions and we're going to revolve those functions around an axis. So one of the things that we see in the lab and that we've talked about is when you revolve a horizontal line around the x-axis, you form a cylinder. When you revolve a semicircle around the x-axis, you get a sphere. All these sorts of shapes are formed by rotating a function and revolving them around an axis. We're going to start out with the x-axis here. When we revolve a region around an axis, we form circular disks. And that starts out because we're rotating the function 360 degrees around the axis. And when you rotate 360 degrees, you're going to create a circular disk with the axis running right through the center of the disk. The radius of this disk is going to be the function. However high or whatever the distance is that the function has from the x-axis creates the radius of our circular disk. And then the integral is going to add up all of those disk areas, just like it did with the Riemann sum. So, to put all that together, the formula for the volume of a solid of revolution is pi times f of x squared dx, integrated from a to b, where a and b are the boundaries of our particular region. So I show you an example below. We've got y is equal to x squared, revolved around the x-axis on the interval 0 to 3. And with the help of Wolfram Alpha, I've got a couple of pictures here that show this. I take that back. This is actually through a different program. So when we revolve this around the x-axis, we get this kind of shape that is kind of like a hat, is the way that I see it. The right shape is it revolved a little bit. So let's take a look at that example. Find the volume of the solid generated when y is equal to x squared as revolved around the x-axis as x goes from 0 to 3. I think it looks kind of like a witch's hat. Other people say that it looks different than that, and there are other things that you might think of when you're thinking of this shape. We call the disks that compose the solid cross-sections. And each cross-section, or the type of shape that cuts through the solid, in this case is an infinitely thin disk, and it's a circular disk. How do we find the volume of such a strange object? Well, we use our formula. Our radius in this case of each of our disks is the height of the function, which is y is equal to x squared. So we plug that in to our formula for f of x, so we get x squared dx. And we're going to square our function, so our overall formula is going to be pi x squared dx, which will then integrate from 0 to 3, as you can see on the very bottom line. This is a sort of problem that you might be expected to do without a calculator. When you integrate this, you're going to get the antiderivative of x to the 5th over 5 times pi, and the final answer is 243 pi over 5 units cubed. Usually units are not asked for in these particular problems, but I included them here just so that you know. Example 2. Find the volume of the solid generated when f of x is equal to 2 over x plus 1 is revolved around the x-axis as x goes from 1 to 3. I couldn't get a very good shape using wind plot on this one, but you get the idea. I got a little picture of it off to the right. So again, we apply our formula. Pi times the integral from 1 to 3 of 2 over x plus 1 squared dx. This is an excellent chance to practice our antiderivatives. We've got 4 over x plus 1 squared, which we can rewrite as 4 times x plus 1 to the negative 2. The antiderivative of that is negative 4 pi over x plus 1, and we're going to integrate from 1 to 3. When you work it out, you end up with your answer of pi. Don't forget your pi in these problems. That's one of the things that people forget a lot, is to multiply by pi when you're dealing with circular disks. Remember, the area of those circular disks is pi r squared, so both parts of the formula need to be included there. Example 3, rotating a solid around the y-axis is not any different, but we need to make sure that our function, our limits, are in terms of y, just like we talked about on the previous reading quiz when we did areas. So I've got an example here. Find the volume of the solid when the region enclosed by x is equal to square root of y, x is equal to 0, and the interval 1 to 4 for y is revolved around the y-axis. I couldn't get Wolfram Alpha to give me a very good picture of this, but essentially the idea is that you've got some sort of a bowl shape. If you kind of tilt your head, you can see how this is revolved around the y-axis. So again, we write everything, including the limits, in terms of y. Notice that our limits are going from y is equal to 1 to y is equal to 4. So those would be the limits of our integral. And we're going to do pi times the integral from 1 to 4 of square root of y squared dy. Everything is in terms of y. We're rotating around the y-axis, just like with areas we oriented with respect to the y-axis. So we get pi y squared over 2 from 1 to 4. We plug in our values. Again, this is something that you can do without your calculator. You get 15 pi over 2. So let's make it a little bit more complicated. We've got what is called the washer method, which is what happens if we rotate two functions around an axis. And we get what's called a washer shape, a washer being the little circular object with a circle cut through it. So, as you can see, I've got a couple of pictures of this. The first picture is another Wolfram Alpha picture. You can kind of see how there's a little hole cut through the center of our shape. The washer is a little bit more demonstrated on the right picture there, where we're taking a function f, we're rotating it around the x-axis. Then we take a function g, we rotate that function around the x-axis. So the way that we want to approach this is the same way as a solid. We get a solid, in fact, when we rotate the function y is equal to f of x around the x-axis, but we want to take out the volume of the hole that's formed when the bottom function, in the case of the right picture, that's g of x, is rotated around the axis. So our formula is we want to find the volume formed when we rotate f of x around the x-axis. So that's the integral from a to b of pi f of x squared dx. And subtract away the volume that we get when we rotate g of x around the x-axis. That's the integral from a to b of pi g of x squared dx. Notice that we are separating our two functions. It's important that you separate your two functions and not combine it into one function and then square it. Keep them separate. We call f the outer radius because it forms the outer radius of our shape, and g is the inner radius. That's the volume that we're going to take out, the volume that's formed by the inner radius or the function g of x. So let's see an example with this. Find the volume of the solid obtained by rotating the region between y is equal to x squared plus 4 and y is equal to 2 about the x-axis, with x going from 1 to 3. So WinPlot has provided us with a nice little graph there of what the two functions look like, and then Wolfram Alpha I've come up with a figure for what the actual shape looks like. Okay, so our outer radius in this case is y is equal to x squared plus 4. It is the function that's farthest away from the x-axis and will form the basis for our solid. The function y is equal to 2 is our inner radius because it forms the little cylindrical volume that's going to be taken out from our solid. So we go back to our formula. F of x is the x squared plus 4. G of x is 2. We plug those in. We find the volume that we get from our outer radius and subtract the volume that we get from our inner radius. You can use your calculator to help you out on this. Remember, our limits are from 1 to 3 because that's defined in the problem. And we get 2,126 pi over 15. A second example, example 5. Find the volume of the wetting band obtained by rotating the region between the graphs of f of x is equal to x squared plus 2 and g of x is equal to 10 minus x squared around the x-axis. In this case, we are not given any sort of limit, so what we need to do, just like with the areas, is find what intersection points enclose our region. We find those by finding the points of intersection. Well, I didn't do the work on this slide, but you can set the two functions equal to each other and find x is equal to plus or minus 2 are our points of intersection. And we proceed just like we did on the previous problem. Our outer radius is the 10 minus x squared. It's farthest away from the x-axis. Our inner radius is the x squared plus 2. It's closest to the x-axis and forms the volume that is getting taken out. You can't quite see that here. You can see the two functions. Wolfram Alpha has drawn the two functions here. The kind of differently shaded region in the middle is the region that's being taken out. It's called a wedding band. I don't know necessarily why, because it doesn't necessarily look like a wedding band. It looks more like a life preserver or something. But that's what a shape like this is often called. Okay, finally, we can revolve around lines that are not axes. And we've revolved around x and y axes up until this point. What happens if we revolve around lines that are below the two curves? For example, horizontal line below the two curves. So our example here, revolve the region enclosed by f of x is equal to 4 minus x squared, our top function, and g of x is equal to x over 2 plus 1, our line, which is indicated in blue on the bottom right, around the line y is equal to negative 2. The horizontal line we're rotating around is y is equal to negative 2. These problems are just like washer problems, except what we've done is we've shifted our axis down by 2 units. Okay? And when you shift the axis down by 2 units, you've increased the areas of each of these regions by 2 units. So what we do is we say the integral from negative 2 to 3 halves of f of x minus negative 2 squared dx. Okay, because we're going to end up adding the horizontal line value to our region already. And we do the same for our g of x. We're going to do pi times the integral from negative 2 to 3 halves of g of x minus negative 2 squared dx. And so eventually we're ending up adding 2 units to our area. When we plug that into our formula and use our calculator, we get a volume of 184.084. Horizontal line above the two curves is done very similarly, but you've got to keep in mind what our outer radius is. In this case, we revolve the region enclosed by f of x is equal to 4 minus x squared, and the same line g of x is equal to x over 2 plus 1 around y is equal to 6, which is a horizontal line above the two curves. So you want to consider what the outer radius is, and that's the function that's farthest away from the horizontal line. Put that largest value at first in the formula. So our outer radius is what's formed from g of x. Okay? And our largest value is the 6. It's our highest y value. So we put that first in our formula. 6 minus g of x squared dx. And we're going to integrate from negative 2 to 3 halves. Don't forget your pi. The inner radius is formed from our f of x. In this case, our f of x is closest to our horizontal line. The largest value, the 6, goes first, so we do 6 minus f of x squared dx. Notice this is different from before where we did f of x minus the line. Here we do the line minus f of x. Okay, that's because the y is equal to 6 is on top. And we integrate both of our volumes, we get 175.105. If we were to do a vertical line to the left of two curves, our idea is that we want to take our outer radius. In this case, the outer radius would be the line x is equal to 2y. And we've got another function, x is equal to y cubed over 4 plus y, which is the red function here. And that's the closest to the line x is equal to negative 2. So we're revolving the region enclosed by x is equal to y cubed over 4 plus y, and x is equal to 2y around x is equal to negative 2. Our outer radius is x is equal to 2y, so we do 2y minus our line, negative 2. And do our same formula with that. And our inner radius, which is y cubed over 4 plus y minus negative 2. And we apply our formula just like we did before. So the farthest away from our line in this case is the blue, x is equal to 2y. Our final formula is 24.056. And finally, a vertical line to the right of the two curves. This is very similar to a couple slides ago. We're going to revolve the region enclosed by x is equal to y cubed over 4 plus y, and x is equal to 2y. Around x is equal to 7. We're going to consider the outer radius as the function that's farthest away from the line. That's the y cubed over 4 plus y. The largest valued function, in this case the line x is equal to 7, goes first in the formula. So our outer radius would give us a volume of 7 minus y cubed over 4 plus y, all squared dy. We're going to integrate from 0 to 2. And our inner radius is the line x is equal to 2y. So we do 7 minus 2y squared dy and integrate that as well. We get a final volume of 32.493.